Kia ora Year 12 and Year 11. This is the first of the 2018 External Level 2 exams that I'm going to YouTube. So I'm going to do these over the next couple of weeks. I've done this first question, which is an excellence question from the algebra paper, because if you're in my class, it's what we've just covered in class today. But it's quite a nice example of how far you can go once you understand the idea of the discriminant. So the question goes like this. We're asked to show that the roots of the equation, and we're given a big long quadratic, can never be equal for any real number k. So if you just think about what we've looked at in class with our different cases for the discriminant, there are different ways to say the same thing. This picture here is one where we have two roots or x-intercepts, one here and one here. And this happens when the discriminant, b squared minus 4ac, is strictly greater than 0. Remember, there are two other cases. This one here, it might look like this, or it might look like this, but it's a situation where we have no x-intercepts. This is the situation where the discriminant, b squared minus 4ac, is strictly less than 0. So the last case is the one that we're interested in here. We're asked to show that the roots of the equation blah 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 can never be equal for any real number k. So I want to talk a little bit about that wording, can never be equal. The case that the question is talking about is one like this, where the parabola just touches the axis. And that's the case where the discriminant is 0. b squared minus 4ac is 0. Sometimes students can get justifiably confused with how we describe that situation. So these are all different ways of saying the same thing. One way is to say that here we've got one repeated root. So if this is x, we'll make up some quick numbers. Suppose this is 2 and it's an ordinary parabola with a first coefficient, an a of 1, then the equation for this one would be y equals x minus 2 squared. Right? So one repeated root, or the other way we sometimes say that is equal roots. Now that wording can put you off, but both of those come from the same idea. That if I wrote out this in expanded form, I'd see that I've got two roots, but I haven't really, because they're both the same. So we either describe that as having one root, or one repeated root, or equal roots. And as I go through the next couple of weeks, I'll probably think of some other wordings that we use, but they're the main ones. And I think that's the hardest part of this question if you're confident with discriminants. So we're asked to show that the roots of the equation can never be equal for any real number k in this equation. So all we have to do now is to find the discriminant and show that it can never be equal to 0. So we want to make sure, if we're doing an excellence question, that we write our communication down really nicely. So we're going to say something like this. So for equal roots, we need, or we require, b squared minus 4ac is equal to 0. And our job is to show that that can't be done. So we go back to the equation, and we've got an a of 1, a b of 2 times k plus 1, and a c of all of that. So we're going to write those out, and then we're going to substitute them into my discriminant formula. So a is 1, b is 2 times k plus 1, and c is negative, in brackets, k squared plus 2k plus 5. Now we substitute them in, and it's going to go like this. Now I've done every little step here. You can skip a couple of these, but you are showing that. So you want to make sure the person reading it doesn't think you've skipped any steps because you didn't know what you were doing. So b squared is this, minus 4 times a, which is 1, times negative k squared plus 2k plus 5. There we go. Now I just have to carefully go through and expand all of that out. So we'll do this, the last bit first, leave that for now, 2 times k plus 1 all squared. Now I've got plus 4 times k squared plus 2k plus 5. That equals, expanding out the first one, 4 times k plus 1 squared plus 4k squared plus 8k plus 20. All we're doing here is just doing one little step after another. We're expanding. Hopefully we're going to make sense of it soon. So that's 4 times k squared plus 2k plus 1 plus this bit. Expanding out this. As I said, you could skip a couple of lines in here if you really wanted to. Some of you watching are probably screaming at the computer screen at this point. All right, so if you're a really confident student, what would I skip? Well, I'd do this line for sure, just to make sure we've got this right. And then I'd do this one to check that I've got that expansion right. I could skip the next one, and then the putting together will go like this. 8k squared plus 16k plus 24. Remember, we're trying to show that this can't ever be 0, and we're just about there. We can take out a common factor of 8 times k squared plus 2k plus 3. Now, it won't ever be 0. How do I think about that? Well, square things sometimes can't be 0. So let's look at this and try to form a perfect square here. Right, so we do completing the square on this. We've got k plus 1 squared. Right, so box that. And we've added in 1, so we'll take out 1. Right, if you're not following that, go watch my videos on completing the square. And now we've got 8 times k plus 1 squared plus 2. Now, can this ever be 0? Well, no, it can't, but we have to explain why. So, for any k plus 1 squared must be greater than 0, right? Except for unless k is equal to -1, right? So we need to put this in here, right? Because if k is equal to -1, we've got this. It could be equal to 0 then, right? We'd have 0 squared, and that's 0. But for any other value, it's going to be bigger. But that doesn't matter because I'm going to add on 2 to it. When I add on 2, it will be greater than or equal to 2. And that means that k plus 1 squared is plus 2 is strictly greater than 0. And timesing that all by 8, it's still going to be greater than 0. So there's no value of k for which b squared minus 4ac equals 0, and that means that no value of k gives equal roots. In other words, if I go all the way back to the top to look at that equation, where are we? Here, this equation will always have a positive discriminant. So no matter what value of k I chuck in there, I'm always going to be in a situation like this where I've got 2 roots. Alright, because we know that it can't be negative and it can't be equal to 0. Thanks for watching. It's pretty early in the year to be looking at this question, so if you're freaking out that that was really, really difficult because you've just seen the discriminant for the first time today, please don't worry, we'll work our way up to them. But I know that a few of you are probably ready for that one already.